Hello everyone and welcome back to PC Retro Programmer. It's been a while since I made a video in this series, and you remember that we're trying to draw the general ellipse. So that's a rotated ellipse on the original IBM PC, so hardware from 1981, and it's something that I don't believe has actually been done reliably in the past. So basically, in order to get going, I wanted to make sure that the algorithm itself works. And you remember that the algorithm starts off by drawing just 8 points, which are the starting points of 8 arcs that it's going to draw. So you can see them here, and it's already tracing out the rough shape of an ellipse here. You can imagine if I join up those points with arcs, then it's going to look like an ellipse. But I ran into some issues at the end of the previous video. Now, I've done this using SDL, which is a graphics library for the modern PC, using the Julia programming language. And of course, when we get onto the original hardware, we're going to do all of this in 8088 assembly language. But when I try to make this ellipse wider, you can see that it's jerking. It's not just increasing the ellipse by 1 pixel at a time, but it's jumping. And this is not what we want at all. So I have actually managed to sort this issue out, and I'll explain a little later in the video what was going wrong. It's not a bug in my code, but it's something that we will need to consider for the final algorithm. So the next thing is that if I make the ellipse a little bit wider here, so you can see all the 8 points again, and start rotating it, at first it seems to be tracing an ellipse, although I'm not sure that the shape isn't changing in some weird ways. And then all of a sudden, the points just diverge and head off in weird directions. And you can see that some very strange things happen. I mean, that's clearly not tracing out the shape of an ellipse, and it's certainly not the same ellipse. And you see that they just sort of flip about and do all sorts of crazy things. So it's a little bit demotivating when this kind of thing happens. And when a whole bunch of issues all occur at once, it can cause the project to grind to a halt. And that's exactly what happened here. But the good news is I managed to figure out what's going on here and what all these issues are about. And so I'm going to show you how I did that in today's video. And I've actually got at least one of the arcs of the ellipse drawing correctly in SDL now. And all the others are basically the same algorithm, so it shouldn't be any problems. And I think we're actually at the point by the end of this video where we should be able to start doing some implementation on the original hardware, which we'll do in the following videos. So let me show you where I was stuck and what was actually going wrong. Well, I realized that if I was going to make any progress with this project, I needed a way to visualize what was going on. And actually, I'm not an SDL graphics expert, and I realized I needed quite a lot here. So it was going to take a very long time to sort out, and it's just a little bit demotivating when just a few simple things that you need are going to take weeks and weeks of work. But then I realized I can just ask ChatGPT to write the code for me. I'm doing this in the Julia programming language, and it writes Julia quite well. And actually, after 4 goes, it came up with this. So you can see that I'm now actually drawing the ellipse that I want to draw using the SDL ellipse drawing command. Now, of course, this is not going to help us on the original hardware, but at least allows us to see what's going on. And in fact, the 8 points that we're drawing, at least when it's in this configuration, are actually on the ellipse, and so that seems to be working. Now, unfortunately, SDL doesn't have a way to draw a general ellipse, a rotated ellipse. It has to have axes horizontal and vertical. So you have to use another trick, basically a rotated texture, in order to draw a rotated ellipse. And that's why it was so technical and complicated to get this working. But fortunately, ChatGPT actually knew how to do this. And there are some other issues here. If you make the ellipse big enough, it looks like the SDL ellipse command itself actually breaks. And I don't know whether this is an issue with SDL or with the Julia wrapper of it, or even an issue in the code that I wrote. I don't think it's the latter, but you never know. So basically, we're stuck with fairly small ellipses here, but this is going to be quite helpful because it already tells us a lot about what's going on. The other thing that I've done is add some code to show some values here. So I've got R is the width of the ellipse, S is the height in pixels. Remember, I set this up so it's 320 by 200 pixels, just like a CGA display. I've got the angle in radians, theta, the angle that it's rotated by, and you can see that changes as I do a rotation here. And I've also added on the left here the 4 values that you need for the equation of a general ellipse, A, B, C, and F. So I want these to be integer values because I'm going to put them in integer registers in the CPU. And I want A, B, and C to fit in 16-bit registers because that's the size of the register on the 8088. And those are the 3 values that are actually used in the main algorithm for drawing the ellipse itself. F doesn't matter as much. There are values that are around the size of F that are used, and I already knew that this had to be very, very large and wasn't going to fit in a 16-bit register, but that's absolutely fine. It'll fit in a 32-bit register. So now that we have all of this, I can actually show you precisely what's going wrong. If I make the ellipse very narrow, which is where the problems were occurring, and I start to increase the width of the ellipse, you can see what happens. The STL ellipse is actually increasing every time I press a key, but the white points, those are the points that we're drawing with our algorithm, those are only moving every so often. So something's definitely going wrong there. And if you look at the A, B, C, F values on the left here, you can see exactly what's going wrong here. Basically, we need fractional values here. The difference between A equals 3 and A equals 4 and A equals 2 is really quite a big jump. Now, I don't want to use fractional values, so why are the values such a problem here? And the answer is that I want all 3 of these to fit in a 16-bit register. So we've already maxed out C here. This is about as big as you can get a positive value in a 16-bit register. And in comparison, A has to be very, very small. And so this is why we can't get all of the values that we need. We've just compressed everything too much. So unfortunately, the answer to this is to increase the size of these values. They're going to need to be 24-bit values. A, B, and C all will need to be 24 bits. If I do a rotation here, you can see that all of them get quite large. So this is unfortunate, but that's just how it has to be. We can probably get away with F being 32 bits. That's not so much of an issue. But that is the first issue sorted out. So let me show you now exactly how I got this code to work with ChatGPT's help, of course. So this is the updated code, and this is what ChatGPT has modified. It's in ellipse3.jl, and you can find that at the link in the description. And I'm not going to go through it in great detail because the whole idea of getting ChatGPT to do this was so that I don't need to know how it works. But there are a few things worth pointing out here. So first of all, to draw the text, we need true type fonts. STL doesn't have its own fonts, and so I had to actually grab the Windows Times New Roman font file, times.ttf, from my Windows fonts directory. And you'll need to do the same if you run this code. I can't distribute that in my GitHub, but you can just go and grab it from the Windows fonts directory and put it in the directory where this program is run from. And the first thing we do, of course, is initialize the TrueType font engine and load up the font. And that's the code for doing that. So the next thing we need is a function for actually drawing a text on the screen. So we've got a particular font we want to use, some text that we want to write on the screen, and the location, the X and Y coordinates. And of course, renderer is where we're actually drawing to at the moment. At the moment, I've got that set to the screen, of course, and it can be set to other things. For example, it can be set to an off-screen buffer. So the idea here is that we're going to draw this text onto a surface. I have no idea why STL has such a complicated system, but I guess if you want lots of flexibility, this is how it has to work. So the fonts get drawn onto a surface, and then you copy the texture, which you create from that surface, onto the screen. And so there are 3 steps to actually drawing this text on the screen. And we need to figure out how big the texture is. So it's a little bit of Julia trickery to get the width and height of the texture, and there's a function for that in STL. We create a rectangle of that size, and then we tell it where we want to put that rectangle on the screen. So that's basically how this works, but any more than that, I don't really want to know. And a little bit further down here, you can see it's added another function for drawing our red ellipse. Again, we're going to draw this on the screen. We want a certain width and height and a rotation angle theta. Now the problem with this is that STL doesn't have a function for drawing a rotated ellipse. Here's the ellipse command here. You can see that it takes color information, a width and a height, and center coordinates, and obviously where it's going to be drawn. So there's no rotation angle here. So the way this works is that it creates an off-screen texture and sets that as the render target, so that when we draw stuff, it's actually drawing it off-screen. We set the color and so on, and then we draw our standard ellipse, the unrotated one, into that off-screen texture. And then we set the render target back to the screen, and then there's this function that STL provides for copying a texture into the current render target, and it has a parameter here for rotation by a certain angle. It takes it in degrees, so we have to convert our theta from radians to degrees, but that actually rotates the texture before it puts it onto the screen, and then we clean up our texture. So that's how we're getting a rotated ellipse, and I think it would have taken me quite a while to figure this out, but ChatGPT did it much quicker. Now the other changes that I had to make were in our ellipse drawing code. Remember, that's only drawing 8 points at the moment. And the first thing that I did is I got rid of the 16-bit values. We're going to use 24-bit values, and the largest 24-bit value that's positive is 2 to the 23. So I go a little bit below that, and I scale everything so that I won't exceed those 24-bit values. I think I had int 16s here before, and I just decided to get rid of those. I'll just use Julia's 64-bit ints for now, just so we don't run it into any problems. Even so, I found that some of these formulas, if I did everything in integer arithmetic first, I could overflow. So I converted to floating point first instead and did the computations in floating point. So there's some changes here. So this is where 4 of the coordinates of the points are computed, and the other 4 points are just reflections about the origin. Now the other thing I've done here is I've removed some corrections for 2 of the points. We're following an algorithm due to Silva, I think from 1989 from memory, and he has some corrections here, and it seems that if I use my equations for computing these coordinates, which I worked out in a previous video, these corrections seem to be wrong. Taking them out makes a whole load of stuff work that wasn't otherwise. And I'll show you in a moment how it looks now. So at first I thought, okay, it must be that the way that I'm computing these points is correct, and De Silva just has a different method and he needs to correct the values. It turns out that it's actually a little bit more complicated than that. I'm going to have to come back to this a little bit later in the video and explain what really was going on here. But for now, this will actually fix quite a few of our issues. So let's take a look and see how this all works now. And here it is, and you can see now that the values get much bigger than they did before. You can see that C value is really quite huge, so that's 24 bits. And now I'm getting a nice smooth movement of the points as I make the ellipse wider. I'll make it narrow enough so that the STL code actually works, and then I'll do a rotation here, and as you can see, all of the points now stay completely on the ellipse. I'll just make it a little bit shorter here so that we can actually see it rotate properly, and everything is staying on the ellipse without those correction factors. So that problem is solved as well. I now have all 8 points actually going exactly where they're supposed to be. And you can see that the right-hand point is always the rightmost point. We've got the topmost point, the bottommost point, and the ones where the slope is at 45 degrees. So it's all working exactly the way we want. The only downside is that we're going to have to use 24-bit values and a 32-bit value. It looks like that's just going to be unavoidable. I thought maybe there'd be a way around this, and I thought through lots of different possibilities, like drawing the ellipse twice as big and scaling it and so on, but everything I thought of still requires 24-bit values. I think it's just an unavoidable fact about ellipses that if you want them to work well, that's what you've got to use. So that's what we're going to stick with. We're just going to have to write some pretty complex assembly language to make that work. So the other thing I want to do now, of course, is to actually implement drawing one of the arcs of the ellipse using the algorithm into Silva's paper and make sure that works, and see if we can spot any additional issues that we're going to face before we start writing code in assembly language. Now, this is Da Silva's paper that we've been following, and we're basically up to this point in the algorithm. We're just about to start drawing pixels, and we actually need to set up some initial values. First of all, we need the coordinates of the very first pixel we're going to draw, and this will be the rightmost pixel of the ellipse, and we already computed its coordinates. In fact, we're even displaying that already. So we'll set x and y to those coordinates. Then Da Silva takes those values and he modifies them slightly to get two values, x in it and y in it, and uses them in these three formulas here to set up three values, fn, fnw, and d1. And these are the main variable values that get used in the algorithm for drawing the first arc of the ellipse. So he's setting up the initial values for those variables. And I'll show you the loop that does that drawing in a moment. It's actually a really simple loop, and that's why we're using this algorithm. And it just depends on three variables and a bunch of constants. Now, there's two different kinds of constants. One set of constants is used to update these values every iteration, and the other set of constants is used to determine when we've got to the end of the arc that we're currently drawing. So he computes all of these in advance for the whole algorithm, not just the first arc. And you can see why I wanted these values to all fit into 16-bit registers. Basically, those are going to be used a lot throughout the algorithm, and it would have been really nice to fit these into a single CPU register, but unfortunately these are the values that we need to be 24 bits. C2, by the way, is just 2 times C. So you can see all of these values just based on A, B, and C, those values that appear in the equation of the ellipse. So anyway, these are going to have to be 24 bits. We'll just have to live with that. Now, there's another problem here that's a little bit more serious, and that is the x init value here. You can see is not an integer. It's a half integer, and it actually matters. So I really don't want to work with half integers. So my solution is going to be to multiply x init through by 2 so that it's 2x minus 1, and that'll be an integer value. And that means that I need to multiply a few other things throughout by 2 to compensate. So you can see x init will have been multiplied by 2, so I'll need to multiply these two other terms here, which don't have x init in them. I'll need to multiply those through by 2 when I set this up. Again, x init is in this term, so I'll need to multiply all the other terms by 2. Fn is the value we just computed. That's already been multiplied through by 2, so no need to modify that. And the most complicated part is actually this third one here. Here, x init is multiplied by itself, and if this was a half integer value, we'd actually end up with a quarter integer value here. We've multiplied through by 2, so that'll now become a half integer value again. And as I said, I don't want half integer values. Now, one way to handle that would just be to multiply everything through by 4 instead of by 2, but I don't want to do that. And the reason is that the extra quarter that occurs sometimes here doesn't actually make any difference. Exactly the same decisions will be made in the algorithm as they would have been if we just ignore that extra 1/4. And so I only need to worry about half integer values here, and because I'm multiplying everything through by 2, this will all be integer. So let's go through it. So x in it we already multiplied by 2, and we've got it multiplied by itself, so that's now multiplied by 4. So we'd actually have to divide this term through by 2. This term's got x in it once, and so that's already multiplied by 2. And the remaining two terms we're going to need to multiply by 2 to compensate. So that's all we really need to do to change this. And of course, all of our constants will have to be multiplied by 2. So let me show you the actual algorithm itself for drawing the arcs. So here's the first arc here, region 1. And you can see that this is a pretty straightforward algorithm. It's just a loop, and every iteration of the loop it draws a pixel. You can see the x and y coordinates of that pixel are changing here and here. And there's really not much to this. It does some comparisons here, and then it just does some additions to update the three values d1, fn, and fnw. Those are those three variables that I talked about. So very, very simple algorithm. And that'll draw the first arc of the ellipse. And the other arcs, there are 4 of them in total, and those are reflected to give 8 arcs. They're all very similar. Now, I did say that that D1 value, if that was out by 1/4, that it wouldn't make any difference here. You can see that if D1 was 0, adding 1/4 to it wouldn't change anything here. It'd still be not less than 0. And if D1 was -1, adding 1/4 to it wouldn't change anything either. It'd still be less than 0. So it doesn't actually matter if we add that 1/4 in. It doesn't change the decision. So we don't need that extra 1/4. And so that's why I can actually ignore that here. So that's basically all we need to do. So I've gone ahead and implemented this in Julia, and I'll show you the code in a moment, and then we'll run it and see what it looks like. For the code itself, there's really not very much to show you because it looks exactly like it does in the paper. Here's that x init value that I multiplied through by 2 to get rid of that half integer value, and I modified the 3 variable values in the way that I explained so that these will all be integers as well. I also just stored that extra 1/4 if it occurs. I don't know that I'll need this for anything, but I'm just keeping hold of that in case I do a little bit later on. And I've also multiplied all these values. These are the constants that are actually used in the first arc of the ellipse. Multiplied all those through by 2, of course. The other thing I'm doing here is I'm keeping track of the largest values that occur in those 3 variables throughout the algorithm. I'm going to print those onto the screen because I want to see how big the values actually get as the algorithm runs, and then we can make some decisions about what sized registers they'll fit into and how big those need to be. So here's the main loop, and really does look exactly like it does in the paper. Here's where we draw the pixel, and the x and y coordinates are being updated here and here. There's the comparisons, and there's the updates to the 3 variables that occur in the first arc of the ellipse. And the only other thing I've added here is just that code to keep track of the maximum values, or the maximum absolute values, of those 3 variables, which at the end I'm just going to print on the screen so that we can see those. So let's run this and take a look and see what actually happens. Well, here it is running, and you can see that the maximum of the 3 variables throughout the drawing of the arc are shown here, and those are very large values. It looks like we're going to need 32-bit values for each of those, which is a bit of a shame, but that's just what it is. So let's expand out our ellipse and see how things change. And yeah, all looks like it's going okay. And I'll just keep it to a size that SDL can actually manage. And you can see over on the right here, we've got the first arc of the ellipse is being drawn between those first 2 points out of the 8. So let's rotate it around, and you can see that it looks like it's working pretty well. Those points are following the ellipse exactly as we expect. Now, every now and again, I can see a little problem here. There's a pixel missing at the bottom here. It doesn't quite meet up with the second point. So that's something that we'll have to look into. That's one issue that we're facing here. And as I go further and further down here, all of a sudden, the arc disappears. It stops going all the way down. So what on earth could be going wrong here? This is a little bit bizarre. Does that mean that there's a bug in the algorithm itself? Well, it turns out there actually are some bugs in the algorithm, but there's actually something else going on here as well. So let's go back to the code, and we'll see if we can figure out what's causing these two problems, the occasional missing pixels and the fact that the arc suddenly half disappears in certain orientations. But let's go all the way around and just see whether it's working otherwise. And yeah, it does seem to be doing pretty much what we want. So if we can just fix those two issues, it looks like we're golden. Well, the first problem turned out to be relatively easy to fix. So this was the missing pixel. You can see that the loop that draws the first arc uses this condition here, y is less than yr. Now, this is the y coordinate, and the problem is that as soon as y equals yr, it doesn't draw any more pixels anymore. And it could be that some of the pixels we need to draw are actually on the same scan line as that final pixel of the arc. And so it will just miss those pixels. So the way to fix this is basically to add an additional condition that the x-coordinate hasn't actually reached its intended target. So if x is greater than the XR, then we still want to keep drawing. And this should fix this issue. Now, the other problem turned out to be a little bit more complicated. It took me ages to figure out what was going on here. And it was those corrections that De Silva has in his paper. Now, first of all, those corrections weren't quite correct in the paper itself. It turns out that De Silva had put a K1 here instead of K2. So I already knew about that issue and I tried putting that in. But De Silva didn't include both of the sign changes for the coordinates in these corrections. And what's actually going on here is that in De Silva's algorithm itself, he only ever uses YNE and XNW. He doesn't use the other coordinates in each case. And because we're actually plotting these points and we're using those other values, we actually need the sign changes for both of the coordinates. We need to reflect the points about the origin before we draw them. And once you do that, and once you realize that that's what's wrong, the points don't wander around all over the place anymore. They actually end up being drawn in exactly the place that they're supposed to. Now, this doesn't affect De Silva's algorithm, but it affects the code that we were using to draw those 8 points, since we're using both of the coordinates in each case. So once we fix those values, let me show you the result. Well, here's the result. Let's just expand our ellipse out here, and we'll make it a little wider until SDL can't cope. Not too bad, that'll do. And let's do a rotation and see what happens. And as you can see, we're not getting any missing pixels anymore, and when we get down here, it doesn't cause half of the arc to vanish. In fact, everything works absolutely perfectly now. So those were the two issues. So there were some issues in De Silva's paper there, no question about it, but they didn't end up being that hard to fix in the end. And now we're in a position where we can go ahead and implement all of this in assembly language. And that, of course, is what we're going to do in the coming videos. Now, of course, we're going to have to work with 32-bit values and 24-bit values and so on. It's not going to be very nice, but we're just going to have to bite the bullet. We found that with the standard ellipse even, that you really need 24-bit values there as well. So it's not too surprising to find that for the general ellipse you need some 32-bit values as well. Anyway, that's it for this week, and we'll get back to this next time, and we'll start looking at turning bits and pieces of the code into actual 8088 assembly language.